Hey everyone, hardware engineers, system designers, welcome to today's Explainer. If you are working with complex integrated circuits, microprocessors, or FPGAs, you have absolutely encountered JTAG. I mean, it's that ubiquitous 4 or 5 pin header sitting on practically every single board you design. But too often we kind of just treat JTAG as this mysterious black box, right? We plug in a programming cable, we hit a button in our IDE, and we just cross our fingers and pray the boundary scan tests pass or the flash memory programs correctly. Well, today, we are changing that. We're going to completely map out the IEEE 1149.1 state machine and really crack open the TAP controller. By the end of this, it's going to be a totally intuitive, incredibly powerful tool in your debugging arsenal. We're not going to view this as some dry, dusty specification. Nope, we are looking at it as a dynamic, deeply logical state machine switchyard. Let's get into it.
Here is our roadmap for today. We'll kick things off with the bed of nails era, move on to the 4 tap pins, and then lay out the TAP state machine itself. After that, we'll break down navigating the instruction path versus the data path, and finally wrap up with updating and executing. Quick and easy.
All right, Section 1, the bed of nails era. Let's get a little historical context real quick on why the industry suddenly needed this complex serial state machine just to test a single chip.
So prior to the 1990s, electronics manufacturing was intensely, literally physical. Think back to the bulky dual inline packages of that era. Testing a printed circuit board meant taking it and literally slamming it down onto a massive bed of nails test fixture. These physical metallic probes would make direct electrical contact with every single pin on every single chip across the entire board. But then VLSI packaging density just absolutely exploded, and we moved to surface mount technology. Pin spacing shrank from 100 mils down to 50 mils, then 25 mils, and even smaller. Chips were suddenly being mounted on both sides of the board. The physical probes? They simply couldn't fit anymore. It was physically impossible. The industry basically hit a brick wall. We desperately needed a way to test the connections between chips and verify internal logic without that physical access. And the grand solution was the JTAG standard, which brilliantly shifted the entire paradigm from physical access to electronic access.
But of course, to achieve that electronic access, we need a gateway. That brings us to Section 2, the 4 tap pins. Before we jump into the state machine itself, we have to define the 4 mandatory hardware inputs that make up the test access port, or the TAP. Think of this little cast of characters as the core of our switchyard metaphor. First up, we've got TCK, the test clock. This is the continuous, chugging engine driving the entire sequence forward. Every single state transition happens right on the rising edge of TCK. Next is TMS, the test mode select. TMS is our switch operator. By simply holding TMS high or low during a TCK rising edge, we dictate exactly which track our state machine takes. And finally, we have TDI and TDO, test data in and test data out. If our TAP controller is a switchyard, TDI is the serial input loading our cargo in onto the conveyor belt, and TDO is the serial output offloading it out.
Okay, with our characters introduced, let's look at the actual map they're going to traverse. Section 3, the TAP state machine.
And here it is. This is the iconic IEEE 16-state logic map that essentially governs every single boundary scan operation in existence. Now I know, at first glance it looks like a dense, tangled web, but let's break it down. Notice the foundational states at the very top there: test logic reset and run test/idle. In test logic reset, the test logic is completely disabled. The chip just acts normally, totally unaware of JTAG. And the design here is brilliant. No matter where you are stuck in this web, if you just hold TMS high for 5 clock cycles, you will safely exit all the way back to the test logic reset state. It's a perfect failsafe. Right below that is run test/idle, which is basically a waiting area where the chip can execute self-tests like run BIST before we plunge into the main switchyard down below.
Now, the absolutely crucial point is how this switchyard is organized. If you draw a mental line straight down the middle of that diagram, you reveal this incredible, elegant symmetry. Over on the right, you have the instruction path, or IR scan. On the left, you have the data path, or DR scan. The instruction path tells the system what to do. It sets the opcode. It essentially tells the switchyard, hey, I want to route my cargo through the boundary scan register, or maybe I want to route it through the device ID register. Once that instruction is firmly locked in, you transition over to the left side, the data path, to actually move the payload through whichever register you just selected. It is so perfectly balanced. If you understand the right side, you automatically understand the left.
Let's see how this builds in practice. Section 4, navigating the instruction path. We're going to hold TMS high, branch to the right, and explore how we actually tell the chip what test to perform.
As we travel down the right side of the state machine, we hit a very specific microsequence. Step 1 is capture IR. What's super fascinating here is that the IEEE standard strictly mandates that the two least significant bits of the instruction register must load a fixed binary 0-1 pattern during this state. This is an awesome built-in integrity check. When you start shifting data out, if you do not see that 0-1, you instantly know your JTAG chain is broken somewhere, period. Next, we step into shift IR. The instruction register becomes a literal conveyor belt connected directly between the TDI pin and the TDO pin. With every rising edge of the TCK engine, we shift our new instruction in, bit by bit. Finally, we hit update IR. We've shifted our data in, sure, but the chip hasn't acted on it yet. In update IR, the new instruction is officially latched and becomes active.
To make this concrete, let's look at what these instructions actually are in the real world. These are real opcodes from AMD UltraScale FPGAs. When you're sitting in that shift IR state, you are feeding in binary codes exactly like these. If you shift in 100110, you're loading the EXT-test command, which completely takes over the physical output pins of the chip for boundary scan testing. If you shift in all ones, 11111111, you are loading the bypass command. That tells the chip to effectively ignore test data and pass it straight through a tiny 1-bit register just to speed up the testing of other chips on the board. The instruction we latch here literally reconfigures the internal plumbing for what we are about to do next. Which brings us right to the payload itself. Section 5, navigating the data path. Now that our instruction is locked in, we return to the top of our switchyard and route our operator down the left side.
Take a look at these steps: capture DR, shift DR, update DR. Sound familiar? It is perfectly identical to the instruction path, but instead of shifting opcodes into the instruction register, we are now capturing and shifting the actual test data payload. For example, if we previously loaded the sample command during the IR scan, then right now during capture DR, the current digital states of all the physical chip pins are instantly snapshotted into the boundary scan register. Then in shift DR, we run the TCK engine to pump all that captured data out through the TDO pin so our test equipment can read it.
The absolute genius of this split architecture is the dynamic routing. At any given moment, only one data register is connected between TDI and TDO. Think about the crazy internal architecture of a modern IC. There might be dozens of different test registers in there, but the shift DR state acts like a master railway switch. Because of the opcode you just set in the instruction path, the data path dynamically routes your serial TDI to TDO connection through entirely different internal chip registers. All the other registers, they just sit completely idle. They retain their state, fully protected from all the shifting data. It's incredibly clean.
Let's wrap up our explainer today by leaning in and looking at some of the really brilliant, subtle safety mechanisms built into the exits of our state machine switchyard. Section 6, updating and executing. Notice those quirky little side loops on both the left and right sides of the state machine? It goes exit 1 to pause to exit 2. Why on earth are these here? Well, imagine you are testing a massive, highly complex board, and your automated test equipment, your ATE, is pumping millions of test patterns into the shift DR state. Suddenly, the tester runs out of fast local memory and literally needs to fetch more data from a hard disk. You absolutely cannot just stop the clock. That could violate system timing and ruin the test. Instead, your switch operator pulls TMS low, dropping the controller into the pause DR or pause IR state. The conveyor belt halts. The test data registers retain their exact state. The test equipment catches its breath, reloads its memory, and when it's totally ready, it asserts TMS high to exit the pause loop and seamlessly resume shifting like nothing ever happened. Okay, I want to end on a question that really separates the novices from the true hardware experts. Throughout this entire explainer, I've been saying that the TCK engine drives state changes and shifts data on the rising edge of the clock. But the standard explicitly mandates that the actual latching of data, the parallel update and update IR and update DR, happens on the falling edge of TCK. Why the half-cycle delay? Think about it for a second.
Here is your aha moment. When data is flying down that serial shift register at megahertz speeds, the register bits are constantly flipping, right? 1, 0, 1, 1, 0. If the active system logic was directly connected to those shifting bits, the chip outputs would be thrashing wildly, potentially causing physical damage or complete system crashes.
So JTAG utilizes a separate parallel shadow register. By delaying the latching action to the falling edge of TCK, well after the rising edge has caused all the shifting chaos to totally settle, it guarantees that only clean, stable, intended test patterns ripple out into the active system logic. It's just a masterful piece of electronic isolation, and it proves exactly how robust and thoughtfully designed this 1990 IEEE standard remains for modern chip debugging. So I leave you with this. Think about that next time you plug in a JTAG cable. Are you just loading a program, or are you the master conductor of this state machine switchyard? Thanks so much for joining me on this explainer, and keep learning.